It's time for us to start fixing the problems with this app. Now, as an important warning first, when you make performance changes, you should change only one thing at a time, then retest to make sure your change helped. If you changed 2 or more things and performance got better, which one worked? Or if performance got worse, perhaps one thing worked and one thing didn't. Let's begin with the table view. We saw lots of yellow when color off-screen rendered yellow was selected. This is happening because the images are being rendered inefficiently. That rounded corners effect and their shadows, they're being done in real time, which is computationally expensive. You can find the code for this in selectionviewcontroller.swift. Down here in cell for row at. You'll see we make a UI graphics image renderer at the size, get an ellipse, ask Core Graphics to clip to that ellipse, and then draw the image inside there. Now, we've used UI graphics image renderer before to make custom rendered images. But this clip call, that's new. Now, as you know, you can create a path and draw to it using 2 separate Core Graphics commands. But instead of running the draw command, you can take the existing path and use it for clipping instead. This has the effect of only drawing things that lie inside the path. So when the UI image is drawn down here, UIKit will draw only the parts that lie inside the elliptical clipping path, thus rounding the corners. The second new technique in this code is rendering layer shadows. If you scroll slightly down here, this code here creates shadows. Now, iOS lets you add basic shadows to any of its views, and it's a simple way to make something stand out on the screen. But it's not fast. It literally scans the pixels of the image to figure out what's transparent, then uses that information to draw the shadow correctly. The combination of these 2 techniques creates a huge amount of work for iOS. It has to load the initial image, create a new image of the same size, render the first image into the second, then render the second image off screen to calculate the shadow pixels, then render the whole finished product to the screen. When you hit a performance problem like this one, you either drop the code that triggers the problem or you make it run faster. In our case, we'll assume the designer insists the drop shadow is gorgeous, so we try and make that code run faster. There are several different approaches we could take, and I want to walk you through each of them so you can see the relative benefits of each. Here's the first possibility. Core Graphics is more than able of drawing shadows itself, which means we could handle the shadow rendering inside our UI graphics image renderer path up here. This closure here. This would mean we don't have to do a second shadow pass later on. To do that, we can use the Core Graphics setShadow method, which takes 3 parameters: how far to offset the shadow, how much to blur it, and what color to use. Now, of those 3, none of those lets us dictate what shape the shadow should be, because Core Graphics has a simple but powerful solution. Once you enable a shadow, it gets applied to everything you draw until you disable it by specifying a nil color. So let's try that out now. We have here the add ellipse call. Before that, I'm going to call setShadow. Let's hide this bar on the right. I'm going to say ctx.cgcontext.setShadow. Like that. And choose the second option. For offset, I'll say 0. No offset. For blur, I'll make it really big, so 200. And for the color, I'll say UIColor.black.CGColor. This is a Core Graphics call, so you've got to use a CG color rather than a UI color. Now we want to draw that shadow before we do anything else. So we're going to go ahead and say, next, ctx.cgcontext.fillEllipse in a rect, and our rect will say is in cgrect. The origin is .0, and the size is our original .size. So draw an ellipse the full size of our image, using our shadow. Once that's done, we can go ahead and disable the shadow. We can say ctx.cgcontext.setShadow. Offset, we're going to do 0 again. Blur will do 0. And color will do nil. And that nil color is what clears the shadow. After that, we'll leave the call to add ellipse, and the call to clip, and the call to draw. Those haven't changed. Now, why do we have to have this blur of 200 points? That's a really, really big blur. And in fact, it's quite different from the blur we had before. This shadow radius, it was 10, and now we have 200. How come? Well, the reason's important, because it highlights another significant problem in the code. The original code down here makes a shadow by saying, give the layer a shadow color of black, make it opaque, make it 10 points wide, and give it a 0 offset. But that's specified in points relative to the size of the UI image view. For our new code, this 200 point blur, that's relative to the size of the image being drawn, which in our case is up here, original.size. So, how big are those images? Well, I'll show you. I'll press Command 1 to go to the project navigator, look inside supporting files, then content, and here are our images. For example, if I look at BTW thumb or IDK large, these are all our pictures here. I'll look at this BTW thumb picture here. Nice JPEG like that. I'm going to right click on this thing and choose Show in Finder. Show me how big this picture actually is. Let's open it up. You can see that's actually a pretty big picture. And the inspector, you can see it's 750 by 750. And that's at 1x size. If you look at multiple sizes, like a 3x size picture, now we're talking 2250 by 2250 pixels. These are huge, huge pictures. Now back in Xcode again, back in our view controller, let's look at the way this thing's made. Up in view.load, you can see tableview.rowHeight equals 90. Our rows are only 90 points high, which means we're loading huge pictures into a tiny space. On 3x devices like a iPhone XS, that means loading 2,200 something pixels squared into a space 90 by 90. But it also means creating a second render buffer that size, rendering the image into there to do the shadowing, and so on. Now clearly those images don't have to be anything like that size, but sometimes you have no control over it. In this app, you might be able to go back to the original designer and ask them to provide smaller assets. Or, if you're feeling ready for a fight, you could resize them yourself. But what if you'd fetch these assets from a remote server and wait until you see the size of the images in a detail view, like IDK large, this thing here. Let's have a look at that. I'll open that in Finder again, open it in Preview. That's 4,000 by 4,000 pixels in size. Now Finder will tell you this thing's only 384 kilobytes. That's a fairly small picture, particularly given that it's 4,000 by 4,000 in size. But in order for iOS to draw those pictures, it has to load the JPEG format and read the raw pixel data out. Because JPEG's highly compressed. That's why it's so small for a huge, huge picture. But uncompressed, to be drawn by iOS, that picture will need at least 45 megabytes of RAM. That's a huge amount of RAM for a single picture. Anyway, let's assume we're stuck with these pictures for now. I'm going to go back to our Xcode window again, and let's just see how our code looks. So our replacement code down here draws the shadow inside our UI graphics image renderer pass, which means now down here, this custom shadow code, that can be commented out. Command/. I'll press Command R now to see how this new version looks. Okay, so you can see the shadowing takes place here. If I go up to the debug menu and choose color off screen rendered, you can see the extra layer of yellow has now gone away, so it's not as yellow as it was. That's an improvement. It means our images are being rendered directly onto the screen. If you've forgotten, I will put that code back again and comment out the new code so you can see how it looked before. So let's now go back to the old behavior. I'll press Command R again, and we'll see how it used to look so you can compare the two. There, you can now see a regular yellow and then a deeper yellow over those pictures on the left. I'll disable yellow for a second, like that. Okay, so that's how our UI used to look. Let's go to the new version again. Oops, like this. There we go. Now, if you look carefully, you'll see it's not quite the same. That's why I've flipped forwards and backwards a few times. If you look at the shadow in our new version, the shadow's square on the right and left edges, like this. So it stops dead on there and dead on there. Let's go back to the old code again. I'll undo that and then comment out these lines of code here and run the old code again. Just compare and contrast how it looks now versus how it used to look. So now the shadows are nice and smooth on the right and left edges. They just go out a nice circle instead. The difference is that with our new code, the shadow being rendered is now properly clipped inside the bounds of its image view, which is probably more technically correct, but it doesn't look the same. And I'm going to assume that this original look you can see now, ugly as it is, was intentional by the designer. So option 1, which is making Core Graphics store the shadow, helps eliminate the second render pass, but it has very different results, and so I think we should rule it out. However, it did at least point us to an interesting problem. We're squeezing very large images into a tiny space. iOS doesn't know or care this is happening because it just does what it's told. But we have more information. We know the image isn't needed at that extreme size, so we can use that knowledge to deliver huge performance increases. Okay, back to the code. I'll leave the original shadowing code in place, and I'm going to scrap the code to do shadowing inside Core Graphics, leaving it with the original closure we had at the start of the program. First, we're going to define a new render size, which will be 90 by 90 in size. That matches the row height we have, so this is the correct size we want the image to actually be. So, we're going to say up here, let renderRect equals a CGRect. For the origin, I'm going to say .0, and for the size, I'll say CG size, with the width of 90 and the height of 90. Remember, those values there are points, so they multiply by 2 or 3 depending on the device. We can now use that size to create a new UI graphics image renderer at the correct size, rather than the original size. That's the 2,500-ish approximately size. We'll replace that by saying renderRect.size. So it makes it a 90 by 90 instead. Next, we'll change this call to add ellipse. It uses a new CGRect from 0 to the original size. We can scrap all that and just say add ellipse in renderRect. That's already a CGRect at 90 by 90. The clip line staying unchanged, but this last line, rather than saying draw at point 0, I'm going to say instead draw in and pass in our renderRect again. Now that will still cause iOS to load and render a large image, but it now gets scaled down to the size it needs to be for actual usage. So hopefully, when I press Command R now, it will still perform much faster. There are pictures, and now I can zoom around significantly faster already. Okay. However, all this is still doing that second render pass, the extra deep yellows right in there. That means iOS is still having to trace the resulting image to figure out where the shadow must be drawn. Now, calculating shadows like this is hard because iOS doesn't know that we clipped it to be a circle, so it needs to figure out what's transparent all by itself. Again though, we have more information. The shadow's going to be a perfect circle, so why bother having iOS figure out the shadow for itself? We can tell iOS not to automatically calculate the shadow path for our images by giving it the exact shadow path to use. Easiest way to do this is to create a new UI Bezier path that describes our image, which is an ellipse with width of 90 and height of 90. Then convert it to a CG path because CALayer, the thing underneath the UI view, doesn't understand what UI Bezier path is. So, back in our code again, we have the shadow color, opacity, radius, and offset. After that, we're going to set shadow path. I'll say cell.imageView?layer.shadow_path equals a UI Bezier path, and this will take the oval in initializer. For its rect, I'm going to say renderRect. That's the size we made earlier, the CGRect, with x0, y0, width 90, height 90. And then It's going to be a CG path, so I'll just put .cg path after the UI Bezier path, like that. Now press Command R again to run the code. And now that dark yellow color has gone, even though you can still see all the shadows. This means we've removed the second render pass by giving iOS the pre-calculated shadow path. And we've also sped up drawing by scaling down the amount of work being done. Working with rounded corners and shadows can be tricky, as you've seen here. If it weren't for the shadowing, we could eliminate the first render pass by setting layer.cornerRadius to have iOS round the corners for us. It's a nice and easy way to create rounded rectangle shapes, or even circles, without any custom rendering code.